Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will explore more on potential energy. If you haven't watched the first video on potential energy yet, go watch it now so that you can understand everything we are talking about. Today we will try to find some analytical expressions for potential energy for a spring, gravity near the surface of the Earth, and gravity at scales where we can't apply that approximation. So let's start. Great, let's start exploring potential energy of a spring. If we have it over here connected to a mass, and this is the equilibrium point at x equals 0, we know that the force a spring creates is equal to minus kx in the i-hat direction in this case. Now, if we take the spring from an initial position to a final position, we move it, we applied some work, we know that work is going to be equal to the integral from the initial position to the final position of f times ds, the displacement. So what we are going to find is that if the displacement is made on that direction, we are going to have this is equal to xi over xf times minus kx dx. We can carry out a simple integration and we find this is minus kx squared over 2 from xi to xf. So substituting those in, we find that work equals 1/2 k xi squared minus x final squared, which by definition we know from our last video it's equal to minus the change in potential energy, which is the potential energy at the final position minus the potential energy at the initial position. Now we need to choose some state for which the potential energy is 0, and in this case the most reasonable thing to do seems to take x equals 0, the equilibrium point. Therefore we are going to say that x equals to 0 is 0. Now if we want to find the potential energy at an arbitrary point, we will take x final to be x and x initial to be x equals to 0. This is the change in potential energy. Now we know this change in potential energy is minus the work. So what we find is minus 1/2 k xi, we have defined it to be x equals 0, so this is 0, minus xf squared, which we have said is going to be x in this case, so it's minus x squared. Now we have some cancellations over here of the minus signs, and we have defined this to be 0. Therefore what we find is that the potential energy for an arbitrary point for a spring it's going to be equal to 1/2 k x squared. Recall from last video that there is not an absolute definition to potential energy. Therefore, by choosing any other arbitrary point to be 0, we could have defined another formula for potential energy, which will be of the form of this plus a constant. Now we'll define potential energy for gravity near the surface of the Earth, as it is simpler. if we have our y equals 0 point over here, and we have a mass that is over here, and then we take it up a little bit to a position at a height, let's say 8, we would need to apply some work, and we know that work is going to be equal to our initial y to our final y of force, that is going to be force times ds. In this case, as we have gravity over here, we know force equals minus mg j hat. Therefore, that makes this expression equal to yi to yf of minus mg dy. A quick integration leaves us with minus mg yf minus yi. Now, we would need to do the same thing as we did earlier. We need to define a point for which the potential energy is 0. And for this situation, the most reasonable thing to do is to find y equals 0 as that point. So we would say that the potential energy at y equals 0 equals 0. And we know that this work, this expression we got over here, is going to be equal to minus u x. Well, sorry, we're not talking about x in here, we're talking about y. So it's minus u y final minus u y initial. So to find what the potential energy at an arbitrary point is, we just do the same thing as before. Minus the change in potential energy from uy minus uy equals 0. It's equal to that expression over there, which is minus mg yf minus yi. We have said y equals 0, so this is 0, this is y, and this is 0. We can cancel the minus signs over there, and we get that the potential energy uy equals mg y. Therefore, the potential energy of that object would be mg times the height. Once again, we could find another expression taking another y point, but the change has to always stay constant. Therefore, whatever expression we find, it will be of the form mgy plus c. Great, now let's explore the potential energy of gravitation. First of all, we're going to draw our planet over here with a radius, and we're going to have an object that is going to be at an initial state at an angle theta and a radius r initial, and it's going to move to a final state at an angle theta prime and a radius r final. So what we see is that the force of gravity, which is minus g m over r squared in the r hat direction, acts in the r hat direction. And if you don't remember this formula, you should go watch part 5 of our classical mechanics series, in which we introduce gravity. Now, as we know it only acts in the r hat direction, we know that work equals r initial to r final of f dot ds. And even though the displacement is not only in the r hat direction, it's also in the theta hat direction, we are going to have only an r hat component. So it's going to be r I rf of minus g m over r squared dr. Now, solving that integral, we can take all of the constants out, and we get it is minus 1 over r from R initial to R final. Substituting the limits, we get that the work is minus dm big M minus 1 over R final plus 1 over R initial. And this is going to be equal to minus the change in potential energy. So minus U at R final minus U at R initial. Now, once again, we need to choose a point for which potential energy is 0. But now, we see that the radius, the relevant quantity we're considering, is in the denominator. Therefore, instead of choosing 0, instead of choosing R equals 0, we're going to choose R equals infinity as our 0 point. So it will be U of R equals infinity equals 0. Therefore, we would get that for an arbitrary point UR, we go from infinity and we get this expression, which is, well, the minus of this expression, the negative change in potential, gives us exactly this expression, and we substitute the initial radius is going to be infinity, so this is going to go to 0, and we are going to have minus 1 over R. Now we need to do some cancellations. This over here is 0, and this minus cancels with that minus. So what we get is that the potential energy at an arbitrary point due to gravity is equal to minus G M over R. And this is a much more simpler expression than if we had to include some bizarre constant over here. For example, if we choose R equals 0 as our 0 point, and even though in that case potential energy wouldn't quite work, as we defined this only for R bigger than the R of the planet, the radius of the planet. Because if not, we will have to take into account a change in the gravitational force, as mass wouldn't be all of it, just some part. So it's better to take R equals infinity and take advantage of that property of potential energy, which is so valuable. That is all for today. I hope this video helped you understand what potential energy is in different situations, but also gain a more deep understanding about what it really means. In the next videos about energy applications, we will use it to simplify some situations in which Newton's law aren't helpful. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button and the bell, follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!